Okay, so next speaker is Sonnenschein, and he will talk about holography-inspired stringy Hadron models.
Okay, I first want to thank Johanna and the other organizers. I hope that you will start it as a tradition now, and every year we'll come in the summer to Würzburg to several days. So I'll tell you about some work that I've been doing in recent years with Doreen Weissman, who is my student and is somewhere around you. So I phrase it in the notion of HISH, holography-inspired stringy Hadron model. We all believe that large n and large lambda is a good description of the physics of n equal to 3 and lambda order 1. Sometimes it's true, and we are familiar with that, but sometimes it's not. Baryons, for instance, of n equal to 3 are quite different than very large n number of baryons, and something else which is less known. Nuclear matter at large n has the form of crystal, of solid, whereas at n roughly less than 8, it is a liquid, so the physics is quite different. Now, what I'll talk today is mainly about the problem with large lambda. Large lambda means that the tension of the flux tube is very big, and it essentially means that we describe a particle rather than a string. And I will want to argue that that is not a very good description of real nature hadron physics. By the way, also lattice simulations of, for instance, Wilson line shows that admit a stringy behavior. Now, this, of course, implies also about the holography that we are using. Holography is basically a relation between string theories and boundary field theories. Everybody usually is doing this map between bulk fields and boundary operators, but as I said a moment ago, that I think is not adequate to describe hadrons. Well, we know that we are used to do Wilson line and 't Hooft lines and Polyakov lines in terms of stringy structures in holography. But my main point is that most of the properties of hadrons, in particular spectra, decay widths, and scattering amplitudes, are also stringy properties. And I don't think that there is any way to get them by doing fluctuations of flavor brains or fluctuations of bulk fields to get glue balls. I've done this myself for several years, but now I realize that that's not, at least I think it's not the right way. And it's, well, the manifestation of that is that the Regge-like behavior of the spectra is a really very basic and trivial property of strings, even classical strings. Apart from the intercept, the Regge behavior is a classical property of strings. And you have to work very hard to get this linearity between m squared and n and m squared and j in a holographic model. I don't think that you really honestly can get it to work. But on the other hand, in a stringy picture, it is trivial. Okay, so I just told you about these issues. Now I'll review what is this HISH model. I'll summarize some of the past results. In particular, I'll show you results about the spectra, about spectra of mesons and baryons, about predictions about glue balls and exotics. Then I'll discuss also decay rates of hadrons, both the theory and some feeds to data. And what I'll tell you, which is new today, is some new aspect that we were working on, and that is the quantization of a string with massive endpoints and the propagator of such strings. And we are now on the way of computing the analog of Veneziano amplitude for this type of hadronic strings. Okay, so the basic construction of Hish is based on the following stages. First of all, we analyze string configurations that correspond to hadrons in holography backgrounds, which I refer to as confining holographic backgrounds. For instance, like the model of Carlos and Maldacena Nunes, Klebanov-Strassler, or the Sakai-Sugimoto models, all these models that have confining Wilson line and have certain other properties which map into confining gauge dynamics. So in these kind of backgrounds, one should analyze stringy configurations, and I'll show you in a minute which ones that correspond to hadrons. Now, the problem, of course, is to go from holographic regime to nature, and that is something that I do not know how to do. So instead, I bypass this issue, and I propose a model, a stringy model in flat 4 dimensions. And you will see it is characterized by these massive endpoints, and in general, the fact that at the endpoints of the strings there are particles, they have mass and electric charge, spin, sometimes baryonic vertex, and so on. And the key issue in this game here is number 5, which is the confrontation with the PDG. I mean, I think that we have to be directed by experimental data. Okay, so what is, let's start with mesons. So what are mesons in holography? This is not yet Hish, just holography. So a meson is a configuration of a rotating string. So it's a string that starts from some flavor brane. This is in the model of a probe flavor brane. And so you have a string, for instance, this will be heavy quarkonium. It starts from this heavy flavor brane, and it goes down, it flattens, it comes up. The flattening is related to this confining behavior. And that's, in principle, we can describe this object also in this holographic curved background, but it's quite complicated. So the idea, for instance, I have some other description of that in the generalized Sakai-Sugimoto model, it will be again a string that starts from this U-shape D8 branes at 2 points, and it rotates. Or another cartoon is of a B-meson. A B-meson is a string that starts from the flavor brane of a bottom and then end up at UOD, a flavor brane. And the key observation is that if you look on the classical equations of motion of this rotating string in holography, it is the equations of motion, if the string is long, are identical. The solutions of the equations of motion are identical to the solution of a rotating string in flat space-time with massive endpoints. And where the masses, these are not QCD masses and not constituent quark masses. These are what I call the string endpoint masses, and they are essentially just the energy or the lengths of, in this curved space-time, of these vertical segments. Now, let's go on and to baryon. So we know that the baryonic vertex can be associated with some wrapped DP brane that wrap P cycle, and there are NC string due to the DBI action of this wrapped brane. There must be NC string coming out, and they can end on the boundary or in a flavor brane, and they can be in various different layouts. For instance, we can have a symmetric layout that the baryonic vertex is in the middle, and there are NC string going from it to the flavor brane. But I want to argue that this kind of asymmetric configuration where we have n-1 endpoints attached to the baryonic vertex and one separate is a preferable one. Now, in the language of NC equal to 3, it's the distinction between the Y shape and a configuration which is a quark-diquark configuration. And there are several reasons why this diquark-quark is preferred. I mean, there are theoretical reasons one can do the analysis, the stability analysis of such configuration. It was done by Truft, and he showed that the Y shape is unstable and you end up with this configuration. But the real reason for that is that the ratio between the alpha prime, or if you want, the string tension between these two configurations, alpha prime of this Y shape should be 2/3 of the one of a straight mesonic string. And in reality, it's not 2/3, it's close to 1. It's up to 5%. It's the tension and the alpha prime of a mesonic and baryonic strings are the same. So you have to think now, from now on, about a proton as a string between a quark and a diquark. Okay, so that's what I just said. In holography, we have this string configuration. It starts with the string at a quark. It goes to the baryonic vertex, and there are two very short strings attached to it. And in Hish, it's just this string between these massive endpoints. One of the interesting things is that the issue of whether the diquark mass is twice the mass of the quark or it's the same mass of the quark, that depends on the stringy configuration. Sometimes we can show, and we show that you find that the diquark mass is the same as the mass of the quark. Now, what about glue balls? There we don't have quarks, so it's very natural to think about them as a rotated closed string. So these are folded closed strings. And they are characterized by the fact, a folded string has a tension which is twice the tension of a single open string, and therefore the alpha prime of it will be half. So that's a very strong distinction between the closed and open string, the fact that alpha prime of the closed string is half the one of the open. And there is another property, and that's the intercept, which I'll discuss in great detail later. For a closed string, it's twice the one of an open string. So I think that with these two properties, we can, I thought that I have another, okay, I don't. But with these two properties, we claim that we show that we can predict the location of higher glue ball states. Now, the last and the fourth example are exotic hadrons, so you can construct all kinds of exotics. In particular, a tetraquark in this model will be built from a string connecting a diquark and an anti-diquark. This is a particular example. And in the Hish picture, it goes into this stringy configuration, as I said, between a diquark and an anti-diquark with various options. Okay, so something is wrong in this. Okay, anyhow. So let me now summarize some of the results that we had in the past. So using this analysis, and I'm not describing now the formula, but just the fits to data. So we fitted a great part of the mesons, starting from these low-lying light quark mesons, and also K star and phi, D and ds, and there is a very nice agreement between the model and the data. I want to emphasize this deviation from linearity, so it's not the Regge trajectory. Linear Regge trajectory is clearly not for heavy bottomonium. You see that there is a very clear deviation from linearity. Now, it applies also for the trajectories of nucleons. In nucleons, for a different reason, we have separate trajectory for even and odd J, but they fit quite well, almost linear trajectories. Now, for glue balls, what we went over all the flavorless hadrons, and we tried to see whether we can fit them all in the trajectories of mesons. It turns out that you cannot. And there is at least a pair, the one that we start with F0 1380, that I don't know if you can see it, but there is here a line which is with twice the slope of the one of the mesons. And there is a prediction also for exotics. This object was identified to decay predominantly to a baryon, antibaryon. That fits very nicely this picture that I showed you of a string connecting a quark, a diquark and an anti-diquark. So we have prediction of if it is such a string, then there will be a radial-like trajectory, and these are the predictions. Okay. Now the second property that we analyzed. So spectra is well known, and it's old story. Everybody recognizes it. Even though I want to emphasize that you won't be able to get this kind of results from QCD, from lattice QCD, or I don't know, for baryons from Skir model. And here they come out very quite simply using this stringy picture. Now, a property which is more complicated to get is the decay width. So if I argue that it's the hadron is a string, then the decay width is just the process of a split of a string into two strings. And to compute the total decay width, we use the optical theorem, and we relate it to the imaginary part of the self-energy diagram, which is complicated to compute. It's an annulus diagram in string theory, but there is a trick that was introduced by Polchinski, where he took one space coordinate and he compactified them, and he let the string wrap it. So we start with an incoming and outgoing strings which are closed, and then they open. And so these are the closed strings, and here they open and then close again. And that is basically just a string amplitude of a disk and two closed string vertices. And that's relatively easy to calculate. So it's just this expression, the integral over the disk of this expectation value of the two vertex operators. And here I denoted the dependence on the length of the string, because that's a property that we wanted to check. And we did, we followed it, and we did a long calculation, but eventually it goes to what Polchinski did, and you end up by having that this amplitude behaves as L squared T, but then the mass squared shift is the amplitude over the energy, which is also L. So altogether you get a result which is in leading order. When you expand these gamma functions, you find that it's linear in the length. So the basic result of string theory, if hadrons are strings, then one should see that the decay width of them is linear with the length. Now there is a relation between the length and the mass of the string. It relates to the mass of the string and also to the massive endpoints, but it's we can have an explicit expression for that, and it can be checked experimentally. Now, what I showed you before was for an ordinary string. Now, with a string with massive endpoints, the story is more complicated because the relation between the length and the mass is more complicated. The boundary conditions are not anymore Newman. It's something that interpolates between Newman and Dirichlet. And also the vertex operators should be modified. This is a part that we haven't done so far, but just assuming that the change in the vertex operator is not dramatic using the ordinary vertex operator, we found that the basic result is that there is a linearity between the decay width and the length of the string. So this is an expression that we found out, and what is interesting is that it is there is a relation, a simple relation with a universal constant. If you want, this is the hadronic string coupling squared. And then you go to the data and you check the relation between gamma and the mass, and you check whether it's indeed universal, and it turned out for the Meson that it's up to 15%, it's really universal. So I believe that that's an indication that hadrons decay in the stringy way. That is another example of what we checked, and that's the decay of excited K star, and again, it fits nicely what the model predicts. Now, in particular, we want to see what is not just the total width of a decay, but a particular decay to a given channel. So in holography, what it takes is that this meson in holography, meson or baryon, it fluctuates, and due to fluctuations, it can hit this flavor brane. So you have to be able to calculate the probability that it will hit a flavor brane, and from that you will get the decay width. So with Maria Zamaklar and Casper Peters many years ago, we've done this calculation, and we found that it behaves like e to the m string, further modified because the massive endpoint, but that's essentially the basic behavior. And this is what underlines this event generator PTIA that describes the fragmentation of a string. So this process, if you repeat it several times, you get this expression with this exponential factor, and that's exactly what people in the experiment are using. The parameters that they fit is a parameter that they got from the data, and they are not the same exactly as what we would get, but the structure is the same. 5 minutes, and I haven't started to describe any results. So I'll do it in 5 minutes. So the question is, how do we quantize this string with massive endpoint? It's a problem that was set 40 years ago by Chiodos and Thorne. They had a phenomenological motivation, and now we came back to it in Hish. So we have an action which is just a string and two particles, relativistic particles, and the endpoints. So this is a non-interacting string. Unlike the ordinary string, which is a free string, now we have an interacting string. And of course, we have to approximate it. So for the fluctuations, we take the quadratic approximation of this square root formula. These are these are the complicated nonlinear boundary conditions. That's the core of the difficulty. These are the only ordinary equations of motion. You can find easily a rotating solution, which translates into the fact that there is a balance between the centrifugal force and the tension. And notice this gamma factor that appears in the tension. But that's what you get. Now you can also calculate net charges associated with the angular momentum and the energy, and you get this parametric expression. This is all classical so far. And when you expand from small masses, you get the linearity of the radial trajectory corrected by these corrections. By the way, comparison with data, we found precisely this 3/2 power. And for large masses, this is what you have. Now, how do you quantize it? You have to introduce fluctuations both in the transverse direction to the plane and the planar fluctuations. And there are also fluctuations which relate to the fact that we are doing a non-critical string. So we have to introduce also the Liouville or the Polchin-Strominger fluctuations. And it's a painful process. We have done it. I want to just emphasize on one aspect, and this aspect is how do you renormalize this result? So the intercept is essentially the Hamiltonian, the worldsheet Hamiltonian, and it relates to the change of from the classical trajectory. So this is the way that the energy and momentum are changed. But of course, you have to renormalize it. Usually we do a zeta function renormalization, which we cannot for these massive endpoints. So we were forced to look for something else. What we found is a procedure that was used before by others, and that is to translate this sum into a Cauchy contour integral formula. This introduces the regularization. How do we do the renormalization? And that I mentioned, I emphasize because I think it's something that can be applied in many other cases. We simply do the renormalization as you do it for the Casimir effect. You take the result of the Casimir energy, or in fact the Casimir force, and you subtract the Casimir force for a string that goes with lengths that goes to infinity. It's just like taking the walls to infinity in the Casimir effect. And when you do this process, it's a contour integral, it's somewhat complicated, but eventually for the massless case, you get precisely this minus 1 over 12, and, or the intercept is 1 over 24. For the massive case, it's more complicated to work it out, but we've done it in the approximation of small masses. So that's the correction. So that it would have been 1 had it been an ordinary string. But now, another point that I want to emphasize is this Liouville or Polchinski-Strominger business, which people did it also for a rotating string with massless endpoints, and it diverges. So Hellerman and collaborators introduced some procedure to renormalize it by introducing a quite ugly counter term. We argue that by putting these masses, they are a regulator, and you still have to do this subtraction, but you get this result that I showed you before. I'll just mention something which I think is not well known, and to me that's the most important problem in the spectra of hadrons. There is a property that the intercept, I told you that's the quantum nature of the spectra. The intercept, if you do it not for the total angular momentum, but rather for the orbital angular momentum, it's always negative. For all mesons, for all baryons, it's always negative. Now, for instance, for the rho meson, the intercept is half, but if you subtract the spin 1, you get minus half, and so on. Now, we don't have yet an understanding of why it's always negative. We try to introduce these masses, in particular, unbalanced masses can yield also negative a region. So these are the two different masses. For instance, a massless and a very heavy guy will result for a negative intercept. Also, charges can do it, and spins. But to get what we want exactly, we still don't know. But this is, I think, the most important problem in the hadronic spectra is to understand why the intercept is always negative. Now we have done also, we are trying now to get, I'm finishing, we are trying to get this modification of the Veneziano amplitude, which is a quite tough problem, but on the way we were able to calculate the propagator. So the general structure of the propagator in string theory has this form, where omega n are the eigenfrequencies. If these omega n's are just the integers, that is the usual log result that we all know. But it's not, these eigenfrequencies are different for the string with massive endpoint. And for the limit of small masses, we argue that that's the correction. And with that, we want now to plug it back to expectation value of vertex operators, which we don't know yet what they are, and calculate the scattering amplitude. So the Hirsch model is, I think, quite successful in deriving hadronic results, which are very difficult to account using QCD. In particular, this Regge-like trajectories, also the decay widths, but still there are a lot of questions to address. In particular, as I said, this negative intercept, and also jet physics, which relates to this fragmentation of strings. So thank you.
Yeah, thank you very much for your talk. Are there questions?
Johanna.
Thanks. You had this one slide about the B mesons with a light and a heavy quark. So I remember, so Nick and I, we were writing papers about this a long time ago, and it's a problem that it's a different scaling with M, N, and lambda than the light or heavy mesons. Did you think
I
about?
didn't understand the question.
So the scaling with N and lambda, in the case if you have a B meson, so then you have a very heavy and a very light quark, so then you have a string between two flavor brains at some distance.
Well, what matters is essentially just the string, and the string is less sensitive to the massive endpoints. It is sensitive, and therefore it's not a linear trajectory, but you get this n squared-like behavior.
Yeah.
So that's a very interesting question. So where does here in all this game 3 enters? In mesons there is nothing in the meson depends on 3. In the baryons, it's the fact that we have a diquark on one side and one quark on the other side. And in fact, it's not very easy to find many experimental results to check the string behavior. For instance, we all know that the E plus E minus goes to Q bar, has this R factor. But here in this game, I still don't know how to introduce this lepton, so I don't know how to address it. But the fact that n is 3 enters here just in this, the fact that n minus 1 is 2, is a diquark. That's the only way that I see it here. Yes?
Further questions? Yes.
By introducing the massive endpoints, can you get rid of the tachyon on the spectrum?
Well, I didn't hear, what did you?
By introducing the massive endpoints, can you get rid of the tachyon in the spectrum?
Well, this issue of the tachyon is exactly this issue of the intercept. If you have a negative intercept, then the Casimir between the endpoints is repulsive and there is no tachyon. And in nature, hadronic strings are non-tachyonic. That's precisely this question of what's the reason that that the intercept or the Casimir is repulsive and the string will never collapse to 0 size and therefore it's non-tachyonic. Now, if you take, as I said, 2 different masses, we will get negative. But for instance, if we have an uncharged meson like pi 0, probably it has the same masses on both ends. So it cannot explain its negative property. But I think that's exactly what I said, that this fact that there are no tachyons in this game, stating differently that the intercept is negative, that's the key issue for these hadronic strings.
Okay. Is there another urgent question? That seems to be not the case, then let's thank him again.